So what we will do for that purpose, right, is that we are going to introduce a new function, right, which is called the widening function, and we will use the widening function to guarantee termination. Okay. So let us see, I mean, so this is the formal definition of the widening function, right. So the widening function, which is denoted by this inverted triangle, right. So this you can kind of you can intuitively kind of think of this as a special form of join, right. So remember this join, right? Join is also a function, right. I mean, in general, pairwise join, right? Join of two elements, you can think of it as a function from D cross D to D, right. So similarly, this widening function is also, it's also a function from D cross D to D, okay. So it takes as input two elements in the abstract domain, returns a new element, but it satisfies certain properties, right. So what are those two properties? So first is that this widening operator, it gives a value, abstract value, which is greater than what is given by join, right. So x join y is less than or equal to the widening operator applied on x and y. And the second important property, right, is that if you have an ascending chain, right, which may not stabilize, right. So if you have an ascending chain x0, x1 and so on, if you construct using this another chain, right, so the second chain y0, y1 is constructed using x0, x1 and so on in the following fashion, right. So y0 is equal to x0 and yn is equal to yn minus 1 along with the widening operator applied on xn, okay. So I have this chain x0, x1, x2 and so on. Now this chain may or may not stabilize, right, we do not know because D may not satisfy the ACC, right. But if you construct another chain, right, where this is y0, so y0 is the same as x0, this is equal to x0, y1 is yn minus 1 and xn, but applying the widening operator on the two, right. So yn minus 1 is y0, which is x0, so x0 and then widening operator applied on x1, then y2 is again, right, so this is equal to y1 and the widening operator applied on x2 and so on, okay. So if you construct this new chain, then this new chain is guaranteed to stabilize, okay. So even though the abstract domain D may not satisfy the ascending chain condition, but the widening function is defined in such a manner that even if you take an infinitely ascending chain, the another ascending chain, right, which uses the widening operator is guaranteed to stabilize. So let us illustrate, right, this widening function for the interval domain. So the widening operator for the interval domain, this is defined as follows, okay. So for so if you have any interval AB, right, then the widening operator applied on AB and the bottom element, right, so this is the bottom element of the lattice, this is just AB itself. Similarly, the widening interval of bot and AB is AB itself. The widening interval of A1 B1 and A2 B2, right, this is defined in the following fashion, right. So if A2 is less than A1, right, so here, right, this is the lower bound and this is the upper bound, right. So we are using this ternary operator, right, which is question mark and colon, to define the lower bound and the upper bound. So the lower bound, right, if A2 is less than A1, then the lower bound is minus infinity, otherwise it is A1 itself, okay. And similarly for the upper bound, the upper bound is computed using B1 and B2. So if B1 is less than B2, then the upper bound is infinity, otherwise it is B1 itself, okay. So this is the definition of the widening operator for the interval domain. So let us see some examples to further understand how this works, okay. So for example, let's suppose I apply the widening operator on these two intervals, the interval 1 2 and the interval 0 2, okay. So if you look at the definition, the definition says that in order to compute the lower bound, right, so for the lower bound you consider the two lower bounds of these two intervals, right, 1 and 0, and if A2 is less than A1, right, so A2, so this is A1 B1 and this is A2 B2, right. So if 0 is 0 less than 1, right, so 0 is indeed less than 1, therefore the lower bound is going to become minus infinity. For the upper bound you ask, okay, is B1 strictly less than B2? In this case that is not so, right, and therefore the upper bound will remain 2 itself, right. So you will get minus infinity comma 2, okay. So this widening operator, right, this is not commutative, and let us see how that is the case, right. So suppose I again apply the widening operator between 1 2 and 0 2, but in the other direction, right. So I take 0 2 widening operator with 1 2. Okay. So again, right, this is a1 b1 and this is a2 and b2. So you ask, okay, is a2 less than a1, right? So a2 in this case is 1, 1 is not less than 0, right? So therefore this is going to remain 0, the lower bound is going to remain 0. And for the upper bound, again you ask whether b1 is less than b2, that is not the case, so the upper bound will also remain 0, will remain 2, right? So you will get 0 2 as the answer, right? So the widening operator is not commutative. Let us do one more example. So what about this 2 3 and 4 6, right? So again you ask for the lower bound, right, is 4 less than 2, right? So 4 is a2 and 2 is a1, right? So 4 is actually not less than 2, right? So therefore this will be, so therefore this will remain 2, and 3 6 you ask whether is b1 less than b2. So 3 is actually less than 6, so therefore this will become infinity, right? So you will get 2 comma infinity. So intuitively, right, I mean what has happened, right, is that so if you look at the right operand, right, so there are two operands to the widening operator, right. So the way that we are calculating the way that the widening operator is defined, right. So if you look at the right side interval, right, the right operand, the second operand, right, to the widening operator, if it contains, right, if the lower limit, right, is less than the lower limit of the first operand, then we simply make the lower limit as minus infinity, right. So if you for a moment, right, think about the join, right. So the 1 to 1 to interval joined with 0 to interval, right. So here you would just take the minimum of these two, right. So minimum of the lower limit, so you will get 0, and the maximum of the upper limit, so you will get 2 itself, right. But now in the widening operator, right, as soon as the lower limit goes down, right, you just make the lower limit equal to minus infinity, right? Similarly, as soon as the upper limit goes higher, right, you just make the upper limit to be plus infinity, okay. So in this case, right, for example, for 1 2 and 0 2, as you move in this direction, right, as you look at the second operand, the lower limit has decreased, right, therefore you just make the lower limit to be minus infinity. Similarly in this example, right, as you go from the first operand to the second operand, the lower limit has not decreased, but the upper limit has increased, right. So as soon as the upper limit increases, instead of taking the maximum of 3 and 6, right, you just make the upper limit to be plus infinity, okay. So this definition of the widening operator, right, this does satisfy the so the way the widening operator is defined for the interval domain, it satisfies the two constraints, right, that we had mentioned earlier, right, meaning these two, okay. Okay. So where does the widening operator play a role? So now in Kildall's algorithm, right, we are going to make a slight change in this algorithm, and this change is highlighted in red, right. So the rest of the Kildall's algorithm remains the same, but as you can see, right, so instead of using the join operator, right, so earlier we used to use the join operator here, but instead of using the join operator, we are now going to use the widening operator, okay. So this is the only change in the Kildall's algorithm, right. So whenever you want to propagate, right, a value from location L to location L prime, right, so you are going to compute this f, right, and then you are going to use this f to update the value at the location L prime, but instead of taking the join with the original value at the location L prime, now you will use the widening operator, okay. And the widening operator, right, is used in this specific order, right, meaning that the first operand is the original value and the second operand is the new value that you have computed. So now let us reuse, right, or rather let us kind of revisit this particular example, but now we will use the widening operator. So we will use Kildall's algorithm with widening, okay. So let us see what will happen here, right. So as usual, we are only tracking the value of the interval I, right, the abstract value associated with the variable I rather, okay. So initially I have minus infinity to infinity at location L0, so you will get 0 0 here, okay. So the 0 0 will then be forwarded to the location L2. Now applying the abstract transfer function of this statement I equal to I plus 1 on 0 0, I will get 1 1, right. So now in the Kildall's algorithm with widening, right, I will use the widening operator, but in a specific sequence, right. So I take the original value at the location L1, which is 0 0, and then apply the widening operator with the new value, which is 1 1. So, if you recall the way the widening operator is defined for the interval domain, right. So, here for the lower bound, right, I will see whether the lower bound has decreased, right. So, the lower bound has not decreased, right, and so then I will see whether the upper bound has increased, right. So, since the lower bound has not decreased, it will remain the same, but the upper bound has actually increased, right. So, therefore, it will just become infinity, right. So, you will get 0 to infinity as the new value associated with the location L1, right. So, now you get 0 to infinity, that 0 to infinity is then propagated forward, right, to the location L2, right, and again you will use the so this assume statement will have no effect because we do not know what is n, right. So, since n in general can also be any value, therefore, the abstract transfer function of this assume statement will also calculate 0 comma infinity, right. So, next you will do the widening operator with 0 0 and 0 comma infinity. Okay. So, again you look at the lower limit has not changed, right, in fact it has not decreased in particular, so therefore, it will remain 0, and the upper limit has indeed increased, right. So, since it has increased, you will take the maximum value, which is in this case is infinity, right. So, not the maximum value, but in this case it is increased, therefore, it will become infinity, right. So, you will get 0 comma infinity. Now, 0 comma infinity, right, applied on I equal to I plus 1, right, you will again get 0 comma infinity, right, and then so therefore, at L1 and L2, right, the abstract values at both these locations have stabilized, right, in the sense that no new abstract value will be computed, right. So, you will get 0 comma infinity at L1, 0 comma infinity at L2, and also 0 comma infinity therefore at LE, right. So, these are the sorry. So, these are the two abstract values, this is the abstract values that you will compute using the Kildall's algorithm with the widening operator, right. So, similarly at location LE as well, you will get 0 comma infinity, okay. And indeed, right, I mean what can we infer, right, using this particular using these abstract values, right. So, what you can infer is that at location L0, the value of I can be any number, but at location L1, L2 and LE, the value of the variable I is guaranteed to be greater than or equal to 0, right, because 0 comma infinity means that it only takes positive values, right, and in fact that is all that you can surmise, right, using this particular program, right. So, because at the end of the program, right, so when this program terminates, the value of I is guaranteed to be greater than or equal to 0, okay, but it can be any value greater than or equal to 0. Okay, so widening, so with the help of widening operator, right, we have seen that this particular, for this particular program at least, using Kildall's algorithm with widening is guaranteed, or rather it will terminate, right. So, and it will terminate with these abstract values, but in general, right, I mean it is also true that the way the widening operator is defined, right, if you take any program, right, if you use Kildall's algorithm with widening, it is guaranteed to terminate, even though the abstract domain does not satisfy the ascending chain condition, right. So, in other words, if you have an abstract domain which does not satisfy the ascending chain condition, but you still want to use Kildall's algorithm, in order to guarantee termination, you must then define a widening operator, right, and the widening operator and then use that widening operator in the Kildall's algorithm, right. So, with the help of the widening operator, you can guarantee termination. However, using the widening operator also has some drawbacks, right. So, in particular you lose out on precision. Okay. So, let us look at this very simple example, right. So, here so while going from location L0 to L1, I assign 1 to the variable I, and from L1 there is a loop, right, self loop which keeps on assigning the value 2. So, but just by looking at the program, right, you can surmise that at the location L1, the value that the variable I can take is either 1 or 2, right. So, it should be in the interval 1 comma 2, right. But if you use widening, right, so if you use Kildall's algorithm with widening, that is not what you will get, right. So, in particular what will happen is that, so once you propagate from L0 to L1, right, so you will get 1 1, right, and then when you propagate from L1 back to itself, right, you will have to use the widening operator with 1 1 and then the interval 2 2, right. So, again by definition, right, for the lower bound, so for the lower limit you ask, okay, has the lower limit decreased? So, it has not decreased, so the lower bound will remain 1, but for the upper limit, right, you ask, okay, has the upper limit increased? And the upper limit has indeed increased, right, it has increased from 1 to 2, so it will just become infinity, right. So using Kildall's algorithm with widening, you will get 1 comma infinity, right. In fact, then you can continue, right. So with 1 comma infinity, you can again propagate that through this through the self loop, right. So you will have again 1 comma infinity, and then the widening operator applied on 2 comma 2. Right. So here again, right, this will also result in 1 comma infinity. Okay. And why is that the case? Because, right, so the way the widening operator is defined, okay, so you ask, okay, has the lower limit increased, sorry, has the lower limit decreased? So the lower limit has not decreased, therefore it will remain 1. You then ask, okay, has the upper limit increased? So in this case, the upper limit has not increased, right, because infinity is greater than 2, but in which case the upper limit will be considered the same, right, so therefore it will remain infinity. So therefore, when you, so if you run Kildall's algorithm with widening on this particular program, you will get 1 comma infinity at the location L1, okay, and that is where it will stabilize. Okay. But clearly this is an over approximation, because I know that at the location L1 I can only take 2 values, right, which is 1 and 2. So in fact, if you had not used widening, right, which means that if you had just used pure join, right, instead of widening, so if you had used the original Kildall's algorithm, you would actually have gotten 1 comma 2. Okay. So here is a trade off, right. So if you want to guarantee termination for any program, then you have to use Kildall's algorithm with widening, but unfortunately that introduces imprecision, right. So what do we do then, right. So now there is a way around, which is through the narrowing operator. Okay. So if so if you use widening operator, you introduce imprecision, but widening operator may be necessary if your abstract domain does not satisfy the ACC, the ascending chain condition, right. So if you want to recover precision, then you can use the narrowing operator, right. So this is the formal definition of the narrowing operator. So just like the widening operator, the narrowing function, this is denoted using this upward triangle, right. So this is another function from D cross D to D, right. And this particular function, right, it satisfies these two properties, right, that so if you have any two elements x and y such that y is less than or equal to x, then this narrowing operator, right, which is x, this triangle y, this particular value, it is greater than or equal to y and it is less than or equal to x, right. So in the sense that it lies between y and x. Okay. And furthermore, if you have a decreasing chain, right, so if this is a decreasing chain x0, x1 and so on, which may or may not stabilize, using this decreasing chain, if you construct another chain, right, which is this y0, y1 and so on, using a similar definition to how we constructed the chain for the widening function, right, then this particular chain is guaranteed to stabilize. Okay. So this particular chain will eventually stabilize. So this definition does not give us any insight. Let us see how, I mean, this narrowing operator is actually defined for the interval domain, right, and then once we use it for an with an example, it will become more clear. Okay. So the narrowing operator for the interval domain is defined in this fashion. Okay. So again, right, so if you have an interval a b, the narrowing operator applied on a b and bot is defined to be bot itself. Okay. The narrowing operator, right, applied on a1 b1 and a2 b2 is defined in this fashion, right. So again, right, the lower limit and the upper limit both are both are specified using this ternary operator, right, question mark and colon. So in order to compute the lower limit, you look at the value of a1, right. So if the value of a1 is minus infinity, right, then the lower limit, right, is going to be a2, otherwise it is going to be a1 itself. Okay. Similarly, for the upper limit, right, so again you look at the value of b1, if the upper limit b1 is infinity, then the upper limit for the narrowing operator, right, is going to be b2, otherwise it is going to be b1 itself. Okay. So this is the definition of the narrowing function for the interval domain. So again, let us see some simple examples, right, to see how this works. Okay. So for example, if you were to compute the narrowing operator for these two intervals, right, 1 3 and 1 2, right, so again you use this definition, right. So in this case, neither of these, so you just look at the first interval, right, which is a1 b1. So a1 is not minus infinity, right, therefore this is going to remain 1, right. So, only if a1 is minus infinity, then you consider a2, right, otherwise the lower limit remains a1, right. So, in this case this is 1, so therefore it will remain 1. Similarly, the upper limit is not infinity and therefore it is going to remain 3 itself, right. So, this, so 1 3 and 1 2, the narrowing operator applied on these two intervals gives me 1 3. On the other hand, let us consider an example which has infinity, right. So, let us say for example, the narrowing operator applied on minus infinity comma 6 and 1 comma 3. Okay. So, here you use this definition, right. So, in this case for the first interval, right, the lower limit is indeed minus infinity. So, therefore, you will consider the lower limit of the second interval, right. So, this will become 1, and for the upper limit it is not infinity. So, therefore, it will remain the upper limit of the first interval, right. So, it will become 6, right. So, you will get 1 comma 6. So, again, right, intuitively if you look at these two examples, right. So, we applied this narrowing function on these two intervals, right. The one thing you should notice is that the second interval, right, this is always contained inside the first interval, right, in the sense that 1 2 is contained inside 1 3 and 1 3 is contained inside minus infinity 6, right. But when you apply the narrowing operator, right, the narrowing operator essentially computes a value, and this value, right, this also includes both of these intervals, right. So, this 1 3 includes both these intervals. In fact, so this value that you compute using narrowing operator, it actually is guaranteed to include the second interval, right. So, 1 3 includes 1 2 and 1 6 also includes 1 comma 3. Okay. Okay. So, now let us try to understand, right, how this narrowing operator is going to help us to recover back the precision. Okay. So, the idea again, right, is that to apply this narrowing operator, but after the widening operator. Okay. So, first you use Kildall's algorithm with the widening operator, right, which we have already done for this particular example, right. So, for this example we ran Kildall's algorithm with the widening operator and these were the abstract values that we got, right. So, at L0 the abstract value was minus infinity comma infinity and at L1 the abstract value was 1 comma infinity. Okay. So, next you will apply the Kildall's algorithm again, right. So, after the Kildall's algorithm with widening operator terminates, right, and it gives you this abstract value, you apply the Kildall's algorithm again, but this time you use the narrowing operator instead of the widening operator. Okay. So, in this particular case, right, what is going to happen, right, is that so at the location L1, right, I have this value 1 comma infinity, right. Now, I am then going to propagate this value through to the location L1 back, right, but by applying the abstract transfer function of this statement, right. So, in particular, so I will compute, so if this is C, right, so I will compute f which is f hat C of this particular statement, right. So, f hat C of where C is the statement I equal to 2 applied on this interval, right, 1 comma infinity, right. So, here if I execute I equal to 2, I will just get 2 comma 2 itself. Okay. So, it does not matter what is the value of I. So, now this new value that you obtained, you use the narrowing operator with this new value and the original value at the location L1, right. So, in particular you will apply the narrowing operator in this fashion, right. So, you will get 1 comma infinity which was the original value at the location L1 and 2 comma 2 which is the new value that you have obtained. Okay. And now you use the definition of the narrowing operator for the interval domain. So, remember the way it was defined, right, was that you look at the lower bound. So, if the lower bound is minus infinity, which it is not, it will remain 1, and then you look at the upper bound, right. So, if the upper limit here is infinity, then you consider the upper limit of the second interval, right. So, you will get 1 comma 2, okay. And so, this 1 comma 2 this will be the new value at the location L1, okay. And again you can apply the same value again, right. So, you can again do the same calculation, right. So, with 1 comma 2 you will again propagate it through this program statement I equal to 2. So, you will again apply the narrowing operator on 1 comma 2 and 2 comma 2, okay. 2 comma 2 is the new value that you will get, right. And again, so if you use the definition, this will remain 1 comma 2. So, in fact 1 comma 2 will be the final value that will be computed using Kildall's algorithm, but with narrowing. Sorry. So, and in fact this is the most precise value, right. So, this is exactly what we wanted, right. So, we wanted to surmise, right, that the variable I can only take values 1 and 2 at the location L1, right. And in fact, we have been able to achieve that by using narrowing pass after the widening pass, right. So, in this way you can sort of get around this imprecision that is introduced by the widening operator by appropriately defining a narrowing operator. Okay. And again, that the way that the narrowing operator is defined, it is guaranteed to give you a sound value, right, in the sense that if you use the narrowing operator, it will give you a sound verification procedure. It will always over approximate the set of actual reachable program states at every location, and it is also guaranteed to terminate, right. So, the Kildall's algorithm with narrowing is also guaranteed to terminate, irrespective of whether the abstract domain satisfies the ascending chain condition or not.